Hi everyone. Now, if you are an old-time user of Raspberry Pi, just like me, and you have recently got your hands on the Raspberry Pi 5, then you must have been noticing that some of your GPIO codes are not working. Not some of them, but pretty much all of them are not working on Raspberry Pi 5. So, if this is something like you, or if you're just starting out with Raspberry Pi 5 but have known something about Raspberry Pi previously, then this video is for you. So what has changed? Why the GPIO codes are not working anymore on Raspberry Pi 5? So what has happened with Raspberry Pi 5 is the fundamental way in which Raspberry Pi handles the GPIO pins has been changed. Now, if you have studied the Raspberry Pi 5 architecture, then you must know that it uses a completely different IO controller called RP1 to handle the IO operations. What it basically means is whatever code that we used to use before using RPi.GPIO will not work anymore, because the way processor is sending commands or sending instructions for the GPIOs to function is now handled by RP1 processor, and this processor communicates with the main processor. Long story short, RPi.GPIO will not work anymore. So what is the solution and how do we go about it? Let's try to see that further. So the official library now and the most future-proof one to use is GPIOZero. Even the Raspberry Pi Foundation is also promoting the use of GPIOZero going forward, and it is also the official library. Now, what changes or why it is future-proof? Because GPIOZero doesn't write the underlying code to interact with the GPIOs. It basically provides a wrapper layer where even the underlying functionality is changed. Even if there is another RP2 processor or anything else that is coming in future, the GPIOZero library can adapt to it, which the RPi.GPIO library was not able to do. So without spending much time, let's try to dive into it and see how to use it. The benefits are object-oriented, less boilerplate. You don't have to do any kind of setup. You don't have to do any kind of pin mode input, pin mode output. You don't even have to clean up your GPIOs. GPIOZero performs the GPIO cleanup on its own. And it's event-driven. Although most of our simple embedded system learning programs or IoT programs will not require you to use the event-driven functionality. But when you are installing Raspberry Pi in an industrial environment where you are doing some IO functions, then event-driven coding or event-driven functionality would be very beneficial. Now, let's see a simple comparison of generating output. Okay, this is purely for comparison. We'll go into details of how to generate the output in a moment. So if you see, what you needed to do with RPi.GPIO was import it as an instance, then you have to set mode, and you have to create it, or previously we used to do this GPIO.BCM to specify the BCM pin numbering. Then for each pin we have to do this GPIO.setup. How do you want to use that pin as output or as input? And then we used to write GPIO.output LED pin, GPIO.high or GPIO.low. This is the old way of doing codes, which will not work on Raspberry Pi 5 and onwards. How to use GPIOZero? It's as simple as this. From GPIOZero, simply import this object called LED, and then you specify this. This is a name, okay? This can be LED, this can be LED1, this can be anything you name. So this is not tied to any specific name, or it should be LED only. So this is an instance of this object that we are creating. So LED is an instance of this LED object, and just specify the pin number in BCM format. Okay, make sure you are only referring to BCM format when you are working with GPIOZero library. And then you simply do LED.on, LED.off. As simple as that. When you terminate your code in the middle of something, the GPIO cleanup is also directly done by GPIOZero library itself. Now, what it does, what happens when we do LED.on, what happens when we do LED.off, we'll go into those details now. Now, look at this code and this schematic to turn on LED when the LED is connected in such a configuration that anode is going to Raspberry Pi GPIO, cathode is going to the ground through a resistor. Now this is how many of us connect the LEDs, and this LED will turn on when you generate GPIO.high in the previous language, or basically when you make that GPIO pin go high, the LED will turn on. Now this is the default state how you can use the LED object from GPIOZero library. So the code goes simply like this: from GPIOZero import LED, and then you create the instance of it, and then you simply do it LED.on, LED.off. This pin over here will make the GPIO pin go high or 3.3 volt, and this pin over here will make it go low or 0 volt. This is the default configuration, but I personally, in all my schematics, have used to using LED in a current sync configuration so that it doesn't damage the GPIO in any way. What it means is, I used to connect LEDs in reverse configuration in all my circuits, development boards, everywhere. How? Something like this, where I connect the LED's anode to 3.3 volt to a resistor. Resistor can be anywhere, doesn't matter. The point is, cathode is connected to GPIO in all my configurations of microcontroller boards as well as the Raspberry Pi boards. So how do you go about this configuration? Again, it's much simpler. All we need to do is, when you are creating an instance of LED object, you need to specify active high equal to false. When we didn't specify anything over here, it means active high is by default true. Active high equals to false means when you do on, it will not create an active high state, it will create active low state, because active high is false. Again, if this technical language is confusing, just try to understand that when you do active high equal to false, this particular declaration will make the pin go low or 0. This particular declaration will make the pin go high or 3.3. So LED actually turns on now here because pin is 0 volt, and in this case pin is 3.3 volt. And look at my configuration here. So when the pin goes 0, the LED will turn on. When the pin goes 1 or logic high, the LED turns off. I hope this should be clear to you. When you experiment on it, things will get much clearer to you. So this is how you can use LEDs with GPIOZero. I have a quick demonstration of the switches as well. So this is how you can use switches. Now, if you don't know, every particular switch connection to any microcontroller, Raspberry Pi, any digital device requires a pull up or pull down configuration, because by default the pin is floating, it's tri-stated. So if I press the switch in this configuration, connect the switch in this configuration, what happens is, when I press the switch, the pin reads 3.3. When I release the switch, we don't know what it reads. So what we need to do in that situation is, either we pull the pin down with a resistor like this, or we pull the pin up by connecting a resistor like this to 3.3 volt. This is common concept across all embedded systems. With Raspberry Pi, the benefit is you have both internal pull down resistor as well as pull up resistor. So you are free to connect your switch in any way. You can connect it against 3.3, you can connect it against ground, doesn't matter. Now let's see with GPIOZero, how can we configure these internal pull ups and pull downs, and how to write down a code for it. Now this is the comparison of reading switch input. Again, this is just a comparison against RPi.GPIO. It's a generic code. All we simply do here is button.waitPress, or if button is pressed, such functions are used in GPIOZero, and you can do your job. I'll directly jump over to the specific codes, so it makes simpler for us for understanding. Now if you look at this, if you have a button connected across ground or 0 potential, then the configuration or the code goes like this: button is equal to button, from GPIOZero import button, that's your object import, Then an instance creation, you can very well call it button SW, X, ABC, doesn't matter, equal to button, the pin number, and then pull up is equal to true. It means if my switch is connected against ground, I want an internal pull up resistor to be true over here. Now, in this configuration, if you write your code like this, if button dot is pressed, it will print button pressed. If you, or else it will say button released. I repeat, button dot is pressed will execute when the switch is pressed, means when the switch is reading logic 0. That is the default state of how button dot is pressed works with GPIOZero. And to do that, if you don't have an external pull up connected, you simply have to write down this line, pull up is equal to true. Now, you may have switch connected like this, where you have a switch connected across 3.3 and you want an internal pull down resistor to be activated. In that case, what you do is you make pull up is equal to false. It will enable pull down resistor. And now the code remains the same. If button dot is pressed, means when you enable the internal pull down, what it will do is it will execute when 3.3 volt is received at GPIO. Otherwise, button is not pressed. You may be wondering, I have not handled it. Like I have not handled whether I have read 0 or 1. That's what we don't want to worry with GPIOZero. When you specify what type of pull up you are using, it understands what type of switch you are connecting. So simply understand that if you have a switch connected against ground, use pull up equal to true. When you have a switch connected across VCC or 3.3, use pull up equal to false. Now let's try to see a demonstration. And I have created my own Raspberry Pi shield for this experiment, which I'll be using over here. And my LEDs are connected in common anode fashion, and my switches are connected across 3.3 volt like this. So let's see a code for them and let's see how do they function. Let me turn on recording with my phone over here. Okay. So let me go to VNC viewer. This is my Raspberry Pi. This is Thorny. Now, as stated, I have 8 LEDs connected on these pins 24, 25, 8, 7, 12, 16, 20, 21. And I have created 8 instances for them. Again, it is not mandatory that you keep them like this. So you can very well call them L1 or small LED 1, doesn't matter. Okay. So all of these are connected in this fashion. Look at it. In a common anode fashion. Means like this. So I need to make the active high false in the code. So all the LEDs are initiated with active high mentioned as false. And then we simply do what? On and off. Now for the sake of demonstration, what I'll do is I'll simply have this code in while true loop. Okay. Now let's turn on the recording. 2 times zoom. The recording is. Now if I turn or if I run this code now, you can see the LED is on and it says on and then off and then on again. Why it's happening? Because I just gave one delay. Let me give another delay here. Sleep 3. So now it will be on for, so you can see on red here, LED is on. Now off for 3, again on for 3. So as you can see, this is a single LED operation. You can just put as many LEDs at the same time as you want. So LED 1 on and LED 8 on. LED 1 off and LED 8 dot off. Let's stop this code. and then run it again. 2 LEDs on, 2 LEDs off. As you can see, both of them on, both of them off. Now likewise, it's your choice. If I want, I can make all of my LEDs go on and off. So 2, 3, 4, 5, 6, 7, 8. And then I will copy this whole into here. And make them off. Let's try to run this code and you will see all the LEDs are on for 3 seconds, off for 3 seconds, on for 3 seconds, off for 3 seconds. Now this is how you will use LEDs. Again, as stated, my switches are connected across 3.3. So let's try a switch code. As you can see, this is a switch test. So because they are connected across 3.3, the pull up setting is made false. And then this code is simply, if SW1 is pressed, it will print that switch 1 is pressed, switch 1 is not pressed, and a delay of 0.5. Let's run this code. You can see it's printing switch 1 not pressed, not pressed, not pressed. My switch 1 over here is this. So let me press this. No, not that, this one. Now as you can see, when I press the switch, it says switch 1 is pressed. When I release the switch, it says switch 1 is not pressed. You can use any number of switches like this. You can use any number of outputs like this with your Raspberry Pi. So this is how you will use the Raspberry Pi GPIO library. What's more, just not the LEDs or switches, the GPIO library gives you motion sensor, LDR, ultrasonic distance sensor, rotary encoder, line sensor, optical devices like LEDs or SPI and I2C devices, many more things. All you need to do is simply go to their official web page as mentioned over here, and then you can see whatever and everything that Raspberry Pi GPIOZero library has to offer. I hope this was informational. Thank you for watching.